Dan Foreman-Mackey. I'm an associate research scientist here at CCA. I sit on the 5th floor. I'm glad I get to go first so I can set the bar appropriately low. So I wanted to spend this time to introduce myself and talk about some of the projects that I'm working on and that I'm hoping to collaborate on. And I put my introduction slide as my GitHub profile because that's where I keep track of all the work that I do. It generally lives somewhere in those 308 repositories, so it can be hard to find sometimes. But so I spend most of my time developing software and methods for data analysis and astronomy. I've spent a lot of time working on Markov chain Monte Carlo methods. I have several projects like Celerite and George for doing Gaussian processes. And then the one that I'm most excited about is this one called Exoplanet. And that lives right here on this website. And this is a tool that I've been developing that's been the focus of my research for fitting exoplanet data sets, but more generally time series data sets, and maybe even more general astronomical problems using modern Markov chain Monte Carlo methods. And the main thing that's special about the methods that are developed as part of this project are that I take advantage of using the derivatives of the model with respect to the physical parameters. And so that can speed up your MCMC convergence by orders of magnitude. So if anyone's done MCMC before, you can, it requires a lot of patience. This can really, really help. If your model is complicated, like actually has like lots of real physics in it and stuff like that, it can be hard to use these methods. It can be hard to compute the derivatives that you need. And so I've been working on figuring out how to do that for exoplanet problems, and that's what lives in this package right here. But if in many cases you would be able to use the tools that I've been working with here, and I'd love to chat if you have an MCMC problem that you're working on that is taking too long and isn't finishing. One thing that I included on the documentation for this project is an introduction to PyMC3, which is the engine that lives behind Exoplanet, specifically worded for astronomers because there aren't really good tutorials, sort of astronomy-specific tutorials for PyMC3. So that can be a good place to start, even if you don't work on exoplanets. And again, I'd love to chat more about that. Okay, so these are some of the things that I like to work on. I'm a huge nerd. And in particular, I've been spending most of my life these days computing the derivatives of functions that are needed for fitting exoplanet data sets. And so I'd love to talk about those things. I'm hoping to actually write a paper about this huge software project that I've been working on this year. And so any encouragement I can get from you, that would be great. Yeah, I'm really excited to collaborate with everyone on anything in this space. I don't have a dog, but I often dog sit Monty. And so I wanted to start the morning off properly with a picture of Monty. Thank you.
Very good. We have 1 minute of questions for Dan, and you all know how to use your microphones. Blakesley.
My friends Steph and Tim.
Is there a question over here?
Does PyMC3, does that use PyTorch for derivatives, or how do you compute the derivative?
Right, so it's built on top of Theano, which is kind of a precursor for those kinds of things. It was developed for deep learning, but it has since been overruled by TensorFlow and PyTorch. So it's sort of legacy software in some ways, but everything that we develop for Theano could be easily propagated through to those other packages. But yeah, I mean, sort of a lot of the derivative work that I've been doing is built on top of machine learning methods and things like that. So, yeah.
Okay, let's thank Dan again.
Good morning, everybody. I'm here in representation of our research group, Brown Dwarfs in New York City, that we have lovingly called out with subway letters, BDMIC there, with the pictures of numerous research members of our team up here. Some of them are giving talks, you'll see. Some of them aren't giving talks, so I encourage you to talk to them. I said this once in the press, and no one's disputed it. We're the largest brown dwarf research group in the world. And that's just down the hall or just down the street in New York. And we're recruiting. So we're looking for people to work on problems with brown dwarfs with us. What's a brown dwarf, you might be asking? I know many people in here aren't studying them. I know because we're the largest brown dwarf research group in the world. They are these objects in between stars and planets that don't quite have enough hydrogen in them to get their core burning. People call them failed stars. I hate the word failure, so I call them overexcited planets. They really bridge the gap in between the star formation process and the giant exoplanet formation process, and so both of those things can be answered with these amazing objects. And I've split the number of projects that we have available that we're recruiting for. And by the way, we're recruiting undergrad, grad, and postdoc right now, all three. So come talk to us if you are looking for work. 4 projects I've broken out for you. One, which I love, is a citizen science project that's called Backyard Worlds. I co-founded that 3 years ago. We have about 150,000 users that are helping us identify very, very, very cold brown dwarfs that are moving. As we, probably me and maybe just me, believe that there's probably a brown dwarf closer than the closest star, and that you could find it if you could find a cold one that's moving fast. We have tons of data that users have already found, and we're looking for people to help us characterize those. These objects have atmospheres that are very similar to exoplanets, and so we now have a project that we're doing that you'll hear from my graduate student Eileen Gonzalez on retrieving the atmospheres of these objects using computational code called Brewster. It's a code that's underutilized right now for exoplanets. We're using it to retrieve the parameters of brown dwarf spectra that are really just like giant exoplanets. We've also got a project with TESS. There's a lot of people interested in TESS here. Ruth's interested in TESS. Trevor David, a postdoc that's coming here, is also interested. All 3 of us have TESS Cycle 2 projects, and we're looking for people to look at the rotation curves of low-mass objects in TESS so we can figure out the gyrochronology relations of young stars near the sun, young stars all the way down into the brown dwarf regime. And then there's Gaia. Gaia is the best. And we've got lots of projects that are mining the lowest mass things that are in Gaia. One of which is looking for accelerating stars between Hipparcos and Gaia that have signatures of a companion. We've been following those up. We got a lot of good stuff there. So we've got data that needs to be reduced, and we've got data that needs to be collected. And so I think I may have 30 seconds left. I wanted to say one other thing, and that is, so you're in New York. Everybody's in this room doing science in New York. One thing you may not realize is that just down the street at the American Museum of Natural History is one of the world's leading, greatest visualization tools, the Hayden Planetarium Dome. And in that dome, with the era of big data that we're in right now, you can immerse yourself in giant data sets. Data sets like Gaia, which is 1.7 billion parallaxes and motions. The picture at the right here is taken from the Gaia Sprint that happened in New York just over a year ago, where we invited everybody to come in, had scientists help us curate a couple of data sets, and built that in so we were flying through data sets. That sounds cool, but it's also the way you can actually investigate your data. So please talk to me if you have data sets you'd like to look at, and have a look at a white paper that I wrote called Ideas about immersing yourself in data experiences in the dome. Stop there.
Questions for Jackie? David? You can do it.
I think it was obvious from what you said, but just to be clear, is it possible if somebody has a data set that they can come and use it in the dome? Is that a facility that you guys provide, or say a few words about it?
Right. So if you have a data set and you want to visualize it and you want to come play with it in the dome, you'd have to come to a person like me, and probably just me, because all the other we have researchers from AMNH, but I'm in the dome a lot. And we have to make your data set work within the software. It's not hard. It's actually something that can be easily facilitated. So anybody that wants to do that, come talk to me. Talk to Ruth or Mordecai as well. Likely they'll probably send you to me.
Thanks, Jackie.
Hello, I'm Megan Bedell. I'm an associate research scientist here at CCA. Woo. I'm interested in exoplanets and stars broadly, and I would consider myself an observer. I spend most of my time looking at data taken from ground-based telescopes, and I have a lot of experience with observing. I am interested right now in this big question in exoplanets, which is how do we find Earth analogs? So there are thousands of exoplanets known, but there aren't any that look exactly like the Earth in that they're Earth size, Earth mass around a sun-like star in a habitable zone type of orbit. So how do we actually get to finding these planets? One thing we know is it's going to be really hard. So this is simulated discovery data of an Earth analog done by student Richard Hall, who's associated with the Terra hunting experiment that CCA is officially part of. And this is optimistic data in one sense of this is 10 years worth of hammering away at a single star every available observing night, which is like half of the year. But it's pessimistic data in another sense of it assumes that we are just using the current state of the art in terms of dealing with things like stellar noise that causes spurious radial velocity signals, and that maybe we don't have the instrumental precision quite figured out as much as we'd like to. So if things stay like this 10 years from now when the Terra hunting experiment wraps up, it's going to be really difficult to find an Earth analog in those data. And those data are like the best chance we have of finding such an Earth analog. But I and many other people are really busy on trying to make that situation better. So there's a lot of things happening here at CCA related to extreme precision radial velocities. EPRV is the jargon for that. Both in terms of data analysis, working with existing data sets. So one thing that I've spent a lot of time on is a open source code called Wobbly that you can ask me about that later. That extracts precise radial velocities from existing data. Such an open source tool wasn't really available in the past. I am currently kind of tinkering away with dealing with stellar spectral variability that is not Doppler shifts, which is a confounding factor. And I'm really excited about working with next generation instruments, which includes planning for the Terra hunting experiment, which again, CCA is now a partner in. So talk to me if you're interested in getting involved in that. We're also starting to work with Express, which is an instrument based with Deborah Fisher at Yale. And starting on Monday, we'll have a pre-doc visiting grad student, Lily Zhao, who will be here for the semester, working with me and David Hogg on Express data. So definitely stop by and meet her next week if you're interested in that. And finally, we're also involved a bit in this NASA NSF working group, which is having a meeting here at CCA in a couple of weeks to talk about next generation instruments. So beyond just radial velocities and finding an Earth analog, there's a lot more that we want to do in the future to really get the most real science beyond just saying there's an Earth. And I'm interested in a lot of aspects of that. So a lot of my background is in stellar characterization. We can use the spectra that we take of stars to find planets to get a lot more information about the stars, including really detailed compositions of them, which is interesting for a lot of reasons. I'm also interested in matching up complementary data sets. For example, the TESS survey, which Jackie mentioned, is a very exciting new entry to exoplanet data and can really give us more than the sum of the parts for this. Related to that, I'm very excited also about Gaia, and I've done work on cross-matching Gaia and looking at possibilities there. And finally, eventually, we'd really like to get to occurrence which is a whole nother complicated question once you take into account all of these different methods. So I will stop there, but I hope I've given you a taste of what we might have to collaborate on. Thanks.
Okay. We have time for one quick question. Over here? No?
Okay, I have a crazy question. Microphone. I have a crazy question. Is there a way of summing the data? I know everything's phase dependent, but can't we, what's the word, search the phases and sum the data in all of these experiments?
Well, all of the
I mean, some across stars, to be clear.
to find like a common planetary system
Yes,
to all stars.
your last point, occurrence rate.
Right. Yeah, it's complicated, particularly for radial velocities, because every system has very different like time coverage and data available. But we should talk more about that later.
Okay, let's thank Megan again. That's a very good dog.
Hi, so I'm Rodrigo Luger. I'm a postdoc here at the CCA. And like Megan and Dan, I'm interested in exoplanets and more generally computational data analysis stuff. Specifically, recently I've been really interested in the mapping problem. So given a time series of a star or a planet phase curve, trying to figure out what the object that generated that light curve looks like. And so the idea here in this case is you have some star, it has star spots on it, and it's got some periodic modulation. I'm interested in the information theory problem behind trying to invert this light curve to find a unique solution to the surface map. It's a really hard problem, it's really mathematically interesting, full of degeneracies. And ultimately, you can see up there, what I'm really interested in is doing this for exoplanets, so trying to get an actual phase curve or secondary eclipses of exoplanets with future generation telescopes to try to map them and someday, find continents and life and things like that. That's very hard, so stars are easier for now, so that's what I've been focusing on. Although on April 1st of this year, Megan Bedell and I and collaborators found a very interesting signal in test data. There was this 24-hour signal that was present in a lot of the light curves, a lot of the pixels of the test detector that corresponded to rotational modulation that we recovered to have, it's a planet, it's the Earth, with, so we called it Sol-D in the paper. But we were essentially able to map the Earth because the Earth is actually illuminating the test detector for a certain part of the orbit of the spacecraft. And that's the map that we got. And if you think about it, what we're really sensitive to is cloud cover. So that's the most reflective thing. The test band passes in the infrared, near infrared. And if you look at simultaneous cloud cover from satellites around the Earth, I claim that we were able to actually detect some interesting features. The most prominent one are monsoon clouds over Southeast Asia. So this was last year in July and August. We were also able to detect clouds over the Congo and clouds over South America. And the oceans roughly correspond to where they actually are. So this is just one application of mapping, and something we may be able to do someday for exoplanets. More recently, I'm also interested in Doppler imaging, which is another technique for mapping stars, typically, where you take advantage of spectroscopic information. So instead of just having a light curve of a star, you have a wavelength-dependent light curve, or time series of spectra. And so, again, I'm interested in the math behind this and trying to find analytic results that allow you to solve this problem efficiently and quickly. And so what I've been experimenting with is using results from my previous papers where I decompose the surface of these planets and stars in terms of spherical harmonics to find analytic solutions to the problem. So given some spot configuration on a star, this is a spotted star, and a spectrum, and the fact that the specific intensity in the spot is lower, what will happen is if the star is rotating fast enough, you have some rest frame spectrum that's blue here. It'll get rotationally broadened, but spot features on the blue shifted side or the red shifted side of the star will cause distortions in the spectral line shape. And so you'll get these orange curves. And so what I'm interested in is going from these orange curves, which are measurements of the spectrum at different points in time, and backing out both what the map of the star looks like and what the rest frame spectrum is. So trying to solve the full problem. And this has been done before, but I think one of the interesting results is that we can now tackle this problem in a very Bayesian and principled way where we can actually simultaneously solve for the map of the object and the spectrum in the case where you don't know the spectrum exactly. So just to summarize very broadly, I'm interested in all these different mapping things. I'm super happy to collaborate with people. I have way too much on my plate right now, so I'd love, graduate students, if you're interested, or undergrads in working on any of these mapping projects, I'd love to chat. So thank you.
We have 10 seconds. Amiel. Maybe not Amiel then. Go ahead. One question. Okay. I have executive authority from Catherine for one question.
That's a great question. So it can be done. It makes the inference problem harder, and we can chat more about it afterwards. That's a great question.
Okay, very good. Let's thank Rodrigo again.
This thing works, yeah. Hi, I'm David Hogg. I don't need this, I think, since there's nothing on my slides. I'm David Hogg. I'm faculty at NYU. I'm also here at the Flatiron, where we work on astronomical data. And I was put in the smallest session because I do work on very small things, but I also work on very large things. I do data analysis at all scales. So we work on the universe as a whole. We also work on exoplanets, all sorts of things. I'm always looking for people and collaborators. So I'm just going to talk about kind of generally what we work on and why. Before I say that, though, I realized something I didn't put in my slides and I should have, is that my group and the larger group of people in New York, and Jackie actually mentioned it, we run hack weeks and sprints and different kinds of ways of different kinds of workshops that are kind of very active working workshops. And we're interested in exploring that and working more on that. So if you're interested in organizing an event that's around hacking, so for instance, Megan mentioned Wobble, we built a whole hack week around inferring telluric problems with spectra. We've also done more general things about Gaia, which Jackie mentioned. So I think I just wanted to say that we are trying to pioneer a new way of building workshops here, and that's part of what we do in my group. My work basically falls into two general areas, which are both very, very methodological. That's why it doesn't make sense necessarily to put me in smallest or largest or whatever, because we work at all scales. One of those areas is working on extremely precise measurements. And I'm interested in anywhere in astronomy where our results are limited by precision. So when you're hitting a precision limit, and of course I got into that through cosmology. I didn't even put cosmology here, but cosmology was really the first area in astrophysics that really pushed precision limits. Right now, the precision things we're working on most hard, one is stellar radial velocities, which Megan just mentioned, and the code Wobble is the first step of a set of projects that would do extremely precise measurements. I'm also interested in measuring the properties of the Milky Way at the percent level. That's now possible. We now have enormous samples of stars, and so we can potentially find the dark matter and the dynamics and the origin of the Milky Way in various ways. And a lot of these things relate to information theory. So my group does a lot of things related to information theory. But they also related a lot to experimental design, and we're working on the design of new experiments. Megan mentioned Terra Hunting experiment. We're also working on the design of SDSS-5. And we've learned in working on these things is that there's a lot of ways to design your survey that aren't good. And there's a lot of ways to design your survey that are good, and so we're thinking about those problems because they affect directly the precisions of the measurements you can make. And then I work in search and discovery, which is very related, but it is a different subject, where we try to find small signals in large data sets, or subtle signals in large data sets. And of course, one is finding planets through transits and radial velocity. Another is we're trying to understand the substructure and the non-trivial kinematic structures in the Milky Way, and they're very subtle in the data, but there's lots there, and we found some things, and there's lots more to find, we can see. And we're trying to find the properties of the dark matter in the Milky Way. And I'm about to show a figure which I showed last year at AstroFest, because these projects take a long time. But I showed you this last year, that this is a thin stellar stream in the Milky Way, and there's a model of that stream, and then there's a model of that stream where we've included a dark matter substructure orbiting in the Milky Way, and we now have radial velocity measurements for many of the stars in this figure, and so we can actually now test whether kinematically whether this is exact what's going on, and put constraints on whether this really is a dark matter substructure and where it is. Thank you.
Perfectly timed. We have a full minute of questions for David Glennis.
With your level of interest and quality of fit, if you just glanced at it, you can see all sorts of defects. And the fit below has this sort of fatness.
Absolutely.
And the one above. So what's your plan for fixing that?
Good.
Is there more information there?
So I have two things to say. That one thing to say, one very general. The question was, that doesn't actually look like a very good fit to the data. And what's, how's it gonna play out? So I would say two things. One very general thing is there's a big difference between accuracy and precision, and a lot of the things we're working on in my group relate to this difference between accuracy and precision, and it's kind of a confusing area, and it has to do with how precise your model is versus how accurate your model is, So there's an issue there. And then the other thing is these stellar structures are extremely complicated objects, and no one has made a model of one of these structures that actually fits at the level of... Yes, yes. Yes, we are pursuing the process of trying to make these really accurate as well as precise. Sorry, I'm over.
That's okay. Thank you very much. Green button.
Oh, great. Right, hi, I'm Adam Germain. I'm a new postdoc at CCA. So I like turbulence and I like stars, and I like understanding how the two interact with each other. And the really nice thing about stars is they have almost no viscosity. So basically any fluid instability you can think of happens somewhere in some star. So I really love this figure. It's by Cantiello and Braithwaite, and what they're doing is they're showing you where stars are convective. So going up is position in the star, and going across is stellar mass. And what you should note here, other than that there's lots of structure and it tracks the opacity and the ionization, is that pretty much every star on the main sequence has a convection zone. And a similar statement is true about almost every type of instability. You can find stars where almost every instability happens. And what I really like about this is that these instabilities matter. They matter both for understanding observations. So for instance, if you're accreting onto your star, you should really care about how quickly the accreting material mixes into the interior. And that's often dominated by things like thermohaline mixing. And so understanding those rates are really important for understanding how to interpret those observations. But it can also affect sort of the actual structure of the star. So there's this problem where stars of sort of 2-ish solar masses, they have convective cores, and these cores seem to require a little bit of mixing extra fuel to match observations. So we need to pull fuel in from the radiative zone into the convection zone. And it looks like what's happening may be that rotating convection preferentially transports heat to the pole. That heat then causes mixing in the radiative zone, which pulls hydrogen into the core again, and you get your longer-lived star. Right. So I do almost all of this mostly from an order of magnitude and scaling perspective, and this means I end up working with stellar evolution codes a lot. So I'm a MESA developer. If you have questions, comments, feature requests for MESA, please let me know. And more recently, I've been thinking about wave mixing driven, so waves that are being driven in a convection zone can propagate out into a radiative zone, and then interactions between those waves can cause mixing in the radiative zone. And also what happens when you have shear in tidally locked systems, or systems that want to be tidally locked but are being pumped away and getting more differential rotation. So if any of this is of interest, and especially if you do simulations of turbulence, direct simulations, I'd really love to talk to you. Or if you want to talk more about order of magnitude stuff, also happy to do that. So thanks.
Okay, we have time for some questions. Mordecai.
There, speak. Okay. Are you doing any multidimensional turbulence modeling using Daedalus or other similar codes?
Not at the moment, but I'd be very interested to.
Amiel, you had your hand up. Very good. Any other questions? Yeah, Jackie?
Can you hear me?
Yeah.
Is this thing on? I don't know these things.
Yeah.
It looked like you were doing G stars in higher mass. So do you have an interest in the lower mass objects, which are awesome and have a lot of turbulence issues?
Yeah, totally. So especially rotation and magnetic fields can play a big role in suppressing convection in the low mass end, and that's something I'm really keen on. I think we don't totally understand how all that works yet, and that could be really important. Yeah.
Any other questions? Ben?
Anything about Rossby modes in hot stars?
Not at the moment, but I'd be interested to know more. Yeah.
Okay, let's thank the speaker again.
Hi everyone, I'm David Kipping. I'm an assistant professor at Columbia University, and I'm going to be a visiting scholar here at the CCA for the next year. Sort of 50% of my time at Columbia, 50% here. So normally I work on exoplanets, but I've always been attracted to weakly informative problems where almost the universe is daring you that you shouldn't be able to do inference, yet somehow you are compelled that you want to do some inference on those problems. Exomoons is kind of an example of that. I think it's a very weakly constrained problem. Another, perhaps even more extreme case of a weakly informative problem is just trying to measure how often do planets have life on them, or how often do those life-bearing planets then go on to have intelligent civilizations on them. Remarkably, this seems like a problem where you shouldn't be able to say anything, because you have one example, one data point, and if you just have one success out of one outcome, that information alone tells you nothing. But there is a bit more than that, and there's actually a timing information. So there was a great paper that was done on this by Dave Spiegel and Ed Turner in PNAS in 2011, a seminal paper on this topic. And they showed that in the timeline of Earth, we have sort of this 5 billion year window for life to get going. And life seemed to have happened fairly quickly. And thus, the naive interpretation of this is that therefore life is easy to get going. And they presented a Bayesian formalism for actually really challenging that naive assumption. They treat it as a Poisson process, so the number of successes is going to be XA here. The number of successes of abiogenesis events is given by some rate. You only care about it having one or more success. It doesn't matter how many times life succeeds. Once it gets going, it's taken over. So we do this, and then we actually have to take a derivative of this if you're interested in the time of arrival. And that's because a Poisson process is defined over a time interval, TA. So it's like a cumulative distribution. So if you actually want to know the time at which life started, you have to take the derivative of this. And then finally, you have to account for the very severe selection effect, which is done by truncating your distribution. So you almost have your likelihood function. The last thing you have to do is account for the fact this is not necessarily, that time there is not necessarily when life began. Life presumably actually began before that. That's just when you see evidence for it in the geological record, unless you have to take a cumulative distribution of this one more time. So you get this beautiful likelihood function. And they do inference on that. I want to go a step further and add an extra data point, which is to think about not just F sub L in the Drake equation when life appeared, but intelligence, F sub I, is another term in the Drake equation. And we do have some information in a similar sense, and that's that we appear here on this timeline. And it kind of bothers me that we appeared so late in the story. There's only 0.6 gigayears to go before we really shouldn't have been able to arise. Photosynthesis will basically stop on the Earth, 600 million years. So does our timing tell us something about how often intelligence emerges? We can do the same trick. I'm going to go through this very quickly because I only have 3 minutes or something left to do this. So you can do a similar kind of formalism. You just say I've got two processes, TA and TB, time of arrival for abiogenesis, time of arrival for intelligence, and they have to satisfy this criterion that both of those events have to happen within a time capital T. You can also demonstrate that this analytic equation is what you get from a Monte Carlo experiment. Just simulate it on your computer, have two processes with a certain rate, measure the distribution of these, and you get a good agreement to this. Then you have to account for selection bias, observational limits as before, which we do here, and you get this magnificent looking likelihood function. This is what it actually looks like if you actually plot it. This is the rate of abiogenesis. It favors white is high, so it favors a high likelihood is happening for high abiogenesis rates. And lambda b, the rate of intelligence emerging, is slow, which kind of makes sense. You can even go a step further and go full Bayesian and use your likelihood function with priors to conduct inference of these rates, which is what I'm doing here. These are the two rates on the bottom. You have to be very careful how you select your priors in these problems. The priors I've selected, I've actually considered f sub I directly. And this is the fraction of planets with intelligent life on them, or the fraction of life-bearing worlds that go on to have intelligence on them. And I'm choosing two priors. One is just a uniform in Fi, which is the dashed line. This is what it looks like in lambda. And then I'm conducting my posterior inference, which is the solid line. So in other words, we get more pessimistic. When you add in how long it took intelligence to emerge on the Earth, you get a more pessimistic outcome than you a priori had. And similarly, another prior that you might consider using is a Jeffreys prior. This is the most uninformative prior you can use for a Bernoulli process like this. This is the dashed line, which kind of curves up at the two extremes. And again, the solid line pulls back towards a more pessimistic view. And if you really want, you can go a step further and say, well, what is the probability of no intelligences? This is the very top right up there. The probability of no intelligences in 262 samples would be less than a coin toss, 50%. And the probability of no intelligence in about 2,000 samples is less than 5%. So this gives you a sense of how many things you'd have to survey for a SETI survey, just conditioned on the fact how long it took us to arrive. So this is very weak inference, but there is a little bit of information in there. This is 2 weeks worth of work since I've been here, so I apologize, it's a little bit dense, but I'm interested in talking to you all about it. Thank you.
Unfortunately, I've been told that
Sorry.
there's no time for questions.
Okay, no problem.
Okay,
Okay.
so thank you, David, and I think we're moving on to the poster.
Oh, is it posted? Oh, let's do one question for David.
Okay, then. Great.
Yeah, you're okay, sure.
and you develop simple life forms, but then there is some physical reason or perhaps even an astronomical reason, for example, that you have to develop an ozone layer to shield the surface from high energy photons, and that process takes time. And so it doesn't look like you folded that in here.
Well, it's kind of folded into the lambda rate. So another way to think about the lambda rate is it's a time scale. The reciprocal of that is the typical characteristic time scale for those processes to take place. So there's a certain number of billions of years for that to happen. Actually, in my last slide, I kind of showed that with these numbers here. So this is sort of the confidence levels on these time scales. So what we're saying is all of that physics is just smashed into that one parameter, lambda, and assuming that all of the planets are essentially identical to the Earth, which is, of course, a huge assumption, and that's what else can you do, then you can say that it can't happen faster than a gigayear, given how long it took us. You're basically saying to 3 sigma confidence, it's very unlikely you could have simple life go to intelligent life based on the time it took us to happen. That would be a 3 sigma outlier event, assuming other planets are representative. We're kind of assuming fundamentally we are a representative sample here. Yeah. Okay, let's do the questions.